Welcome back, everyone. So, today we'll discuss a problem from thermodynamics, and I picked up this problem from Pathfinder book, and it's from Build Up Your Understanding section. It's question number 28. So, let me read out the problem first. Some amount of nitrogen gas is filled inside a vertical cylindrical container under a massive piston that can slide in the cylinder without friction. The inner surfaces of the piston and the container are coated with a perfect heat insulating material. The whole assembly is inside a highly evacuated chamber. That means basically P outside is 0. That is the purpose of giving this line. If the piston is struck to impart it a velocity u downwards, after a large number of oscillations, the piston comes to a complete stop. Find the displacement of the piston. Okay. So figure is also given. It's quite well understood, I guess. And so basically this question tests your understanding regarding reversible and irreversible process, right? So let me explain the difference between two processes in a brief. Basically, in reversible process, in each intermediate step, we can define the state variables, means the pressure, volume, temperature, all are defined. And we can do that because it is a quasi-static process, right? Quasi-static means at each at each point, the equilibrium condition is maintained. Be it thermal equilibrium, be it mechanical equilibrium, it is maintained. Means mechanical equilibrium means the net force is obviously zero on the system. So, or you can, if you call it as a very surface level, you can define the reversible and irreversible process without all this physics terminology. You can call that reversible process is quite slow, right? So whatever be the process that is happening in very slow manner, that is a rough definition, obviously not technically true, but I am telling you to just for your quite better understanding, is reversible process. And the process that is happening very abruptly, very fast, that is irreversible process. And in irreversible process we can't define the state variables, obviously in intermediate steps we can only conclude about the initial and final condition. Let me show you here one example. Let's say this is a PV plot and A to B, this is one process. So at each point we know the value of pressure and volume, and if we know pressure and volume, temperature is obviously defined by default. So it's a reversible process, right? Here you can comment on each step of this process. But in case of irreversible process, we can only conclude about point A and point B, and we will have no comments regarding this intermediate steps. We don't know how it is happening. We are only concerned about the initial and the final conditions for irreversible process, right? And we can't define the state variables in between. Yeah. So this is one brief definition or distinguish, whatever you can call, between two processes, and other things we'll explore in the solution. Okay. So in initial and final state, obviously there was one hint, right? I have marked it with highlighted that if the piston is struck to impart it a velocity u downwards, obviously if you suddenly give a velocity u downward to the piston, it will abruptly move downward, and from there you can conclude that it's a irreversible process, and that is very obvious. But in initial and final conditions, the piston is in equilibrium, so we'll have the net force in the piston 0. One force is always the gravity, I mean the weight of the piston mg downward, and the other will be pressure of the gas times area A of the area A of the cross section. So to maintain equilibrium, obviously mg will be equals to P naught times A. I have assumed the pressure of this gas as P naught here, and I will also claim that the pressure will remain P naught in final state as well, because there is only one force, pressure times area, that can nullify mg, and as mg remains constant, so to balance mg, pressure should be constant, okay, in both the cases. So yeah, I have shown here that it's also irreversible process. Okay, so let me tell you that in these kind of problems, irreversible problems, in maximum cases we will apply the work energy theorem on the piston. We will take piston as the system and we will apply work energy theorem. So in maximum of the cases it will work. Obviously you can try this method. There are many problems in Pathfinder, right, related to irreversible problems. Generally we don't deal with irreversible problems, but it's a quite an interesting one, and many such problems are there in Pathfinder. You can try with the same method. Same method means this idea to take the piston as the system and apply work energy theorem. That will be one of the best solutions for this kind of problems. Okay, so applying work energy theorem on the piston, there will be two works: work done by gravity and work done by gas will change its kinetic energy. If finally it is at rest, so kinetic energy is 0. Initially it was half mu square. Work done by gravity is obviously minus of mg times hf minus h. Okay, so let me tell you here that hf, I've assumed the height of the piston from base in final condition. It is obviously the final diagram, and obviously the given one was initial. So initially it was at a height of hi. So mg force gravity is downward and hf minus hi is the displacement upward. That's why there is one minus sign, as force and displacement are opposite to each other. And there is one term of work done by gas. That is quite interesting one. We can't directly apply the work done by gas formula that you may think that we can directly apply, because we memorize the formula of work done by gas in an adiabatic process, right? It's an adiabatic process definitely, because Q is 0. We have not supplied any external heat. Yes, it's an adiabatic process, but remember it's an irreversible adiabatic process, not a reversible. All the standard formulas that we use, I mean the work done formulas for isothermal, adiabatic, isobaric, these all are valid for reversible, right? We don't often call this that these formulas are for reversible adiabatic, this is for reversible isothermal, but it is actually for reversible. That reversible term is quite self-understood. So we can't directly apply the formula, but we have a method to find out the work done by gas in irreversible process as well. So I have shown that calculation on the right hand side using this blue ink. So first law of thermodynamics is obviously valid, because this comes from energy conservation principle, right? This is irrespective of reversible or irreversible. And as Q is given to us 0, we'll have work done by gas is equals to minus of delta U, that is change in internal energy of the gas, and that will be NCV delta T delta U, and this is the CV for diatomic, as nitrogen gas was given to us, right? N2 is diatomic, 5R by 2. So this comes out as minus 5 by 2 NR delta T, and again PV equals to nRT. The ideal gas equation is only valid for initial and final steps of irreversible process. If it was reversible, you can apply this equation at each and every intermediate step, but for irreversible process it is only valid for initial and final condition. Okay, so we are supposed to find out the change, so we'll take differential both side, that is delta PV will be delta of nRT, should have been written, but as N and R are constant, I'm keeping it outside, it will be only delta T. So that is what I have written here. And delta, again in delta PV, pressure is also constant. I have already explained to you that initial and final pressure both are P naught as per our assumption. So it will be basically P naught times V final minus V initial. V final minus V initial will be area of cross section times H final minus H initial, because it is in cylindrical shape. This is what I have written here, and that is my value of work done by gas. I have put that in the first equation that we are solving from work energy theorem. Yeah, so the equation turns out like this, and now we'll use this one, that mg equals to P naught times A. So we are substituting P naught times A as mg, and we'll get here one minus 5 by 2 and minus 1 times mg delta h. So total it will be minus 7 by 2 times mg delta h equals to minus half mu square. Minus minus gets cancelled, m by 2 gets cancelled. Delta h turns out as u square upon 7g. So this is the displacement of the piston, and that's the answer for our question, that u square by 7g amount of change in height will occur in the piston, and that is basically the displacement. Okay, so that's all for this problem, and it was basically to make you understand the difference between reversible and irreversible process, and to make you familiar with irreversible process, because as I said, in JEE domain we generally don't get many questions regarding irreversible process. So you can try out few more irreversible process related questions from Pathfinder, or I will take up a few questions as well in near future. Okay, that's all for today. Thank you.